Welcome back. This is the second video on waves. So far we've covered reflection. Now we're going to have a look at refraction. So coming down here, let's have a look at refraction, the syllabus objectives you need to know. So here they are. So starting off with the number 1, which is describe an experiment to demonstrate the refraction of light. Well, we did the experiment. Remember, we put light through a glass block, as you can see here, and when the light entered the glass block, you'd expect it to continue on straight like this, but no, it's actually bent by that angle there to travel on this path along here, whoops, which is called refraction. So this bending of light, this happens here and here, we call that refraction, and it's where light changes direction. Now, why does it change direction? So the definition of refraction is change of direction, and this happens because of a change of speed of the light. So as it enters the glass, it slows down. Kind of makes sense. Well, the actual reason why it slows down is quite complicated, but think of it like this. Glass is much denser, there's many more atoms, it's harder for the light to get through. If you had to walk through an empty room, that'd be quite easy. Fill it with a load of year 9s, it's going to be a bit more difficult. So it's kind of like that. The glass atoms are much closer together like this, so it's harder for the light to get through. Whereas air, the atoms are spaced out like that, it's much easier for the light to get through. A bit more complicated than that, but that will do. So the change of speed of light, that's caused by a change in optical density. That's how basically dense the material is to the light. So that's refraction. And there's 2 angles that we're particularly interested in, which are shown here. Remember, this is the ray coming in. This is this ray after it's crossed this interface or boundary between air and water. If both materials were air, you wouldn't get refraction because there's no change in density and there's no change in speed. But because water is more optically dense, the atoms are close together, the light slows down and it therefore bends, as we can see happening here. How do we know it's bending? Well, remember, just continue the ray on. It should be like that, but it's actually bent to there. So, So, what are these angles called? Well, the first one, as before, because it's the ray coming in, it's called the angle of incidence. And you can either label that I, or often now we're going to label it as this, which is theta, which is symbol for angle, and we number it number 1, because that's the material that the light is first in. So this is material 1, because this is where the light starts, and this is material 2. This one, well, go on, have a guess. Last time it was called angle of reflection, but now we're doing refraction. So you guessed it, this is physics, things make sense. It's called the angle of refraction, and it gets its own symbol. And being physics, we're not that inventive, we're going into material 2, so we call it theta 2 or angle 2. It's also called R as well, which is a bit confusing, so I prefer using these 2 notations here. So we've talked about experiments, and we've kind of introduced you to this terminology. Remember, we're using this symbol and this symbol. You can use I and R as they do in your syllabus, but it can get more complicated. It says describe the passage of light through a parallel-sided transparent material. That just means a glass block that looks like that. So we'll just talk about that, and then we'll come on to these equations here and a definition, of the refractive index, which is n. So zoom out and go down here. Let's look at light traveling through a parallel-sided glass block. Now, as the ray comes in, it's always good to still draw the normal. And remember, this is right angles to the surface where the ray hits the surface. So that's the normal. And remember, always useful. This angle, as we said, was theta 1. It's the angle of incidence. Now, if it's going into glass, it's going to slow down. And if it slows down, it bends towards normal. Towards the normal. That means it goes like that. So it's bent towards the normal. It should be up here somewhere, like this. But no, we bent it towards the normal because it's slowing down. Reason being, remember, was that car analogy, driving onto the sand. That's one way of thinking of it. If you're not sure about that, do ask. Right. As it hits this interface, again, you can draw another normal because refraction is going to happen again. This angle here for the first ray, this would be the angle of refraction. And then this angle here would be the angle of incidence the second time over. So remember, you can have 2 cases of refraction, each with their own angle of incidences, each with their own normals, each with their own angles of refraction. Now, the key thing is when it comes back out, because it's going back from glass to air, it actually comes out parallel to the initial ray, and that's important if you're drawing this in exam. So I'd expect it to be somewhere over there. And don't forget to put arrows on to represent the direction. So that's what happens when light goes from air to glass to air. Notice at this interface, we're now going air to glass. So that means the light speeds up. So the light's going faster. And in this case, when it speeds up, it bends away from normal. Okay, you need to learn that. What does that mean? Well, again, as I said, if the ray was not bending, it will continue along this path here. But actually, you can see it's bent away like that from the normal. So that's because it's sped up. Let's now look at Snell's law. Now, if you remember going back up to your syllabus up here, it's written as sin I over sin I equals n. Now, that's one way of learning it, and it's worth learning it. Oops, sorry, it's so messy. There we are. So sin I over sin r. Remember, sin is that mathematical function on your calculator, which you would have done when you did trigonometry maths. Now, remember I, or theta 1, and r, or theta 2, so that's the angle of incidence and the angle of refraction. Now, what is n? Well, n is something called the, I'm going to give it a cool coloured pen because we haven't used this in a while, the refractive index. This is basically a ratio, and it tells you how much light slows down by, and therefore how much it bends by. To calculate the refractive index, you can use this equation here, n equals c over v. C is the speed of light in a vacuum. Okay, now what is that? The speed of light in a vacuum? Well, it's a constant. It's 3 times 10 to the 8 meters per second. You need to learn that, by the way. And v is the speed in the material. So let's say we're studying glass, and we want to know the refractive index of glass. Well, you put the speed of light in the glass. If it was water you're interested in, it would be the speed of light in water. You can see why it has no units, because speed of light is in meters per second, and speed in the material is also meters per second, so the units kind of cancel out. It's unitless, it's a ratio. It tells you how much light bends by. Remember, a higher refractive index, so higher n, equals more bending. So it tells you how much the light bends by. If it's higher refractive index, the light's going to bend more. To work out the refractive index, you can use this equation. So we could use that equation as I just mentioned, but this one here is much better. This works in any situation, whether you're going from diamond to water, air to glass, it always works. Now, what do we have here? Well, we have N1. Now, the 1 in this place refers to material 1. So, if we were going from, let's draw a boundary there, and the light's coming this way and it's bending that way. 1 refers to the material where the light starts. 2 refers to where the light ends. The angles, theta 1, remember, is the angle of incidence in material 1. 1, again, makes sense. And theta 2 is the angle in material 2. So the angle of refraction. So you use the refractive index of material 1, the refractive index of material 2, and the two angles, and they're related using this equation. Remember, if you ever need to find an angle, once you rearrange that equation, and I can do some videos on how to use this equation in more detail, but say you have sine theta equals 0.725, excuse me, my pen's going a bit crazy, 725, then remember you need to inverse sine, so you click shift sign on your calculator, that number to actually get the angle. So, let's now look at total internal reflection. Okay, so we're going to look at total internal reflection now, which I'm going to shorten to TIR. Careful, it's total internal reflection, not refraction. So I don't want to say that in the exam. And you can't write TIR really in the exam without stating what it is first. This is it here. You can see it happening here, 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 and here. And it's where the light reflects at a boundary where you'd think it will actually go on to refract. Now, why does this happen? Well, if we look at these images here, let's start with image 1 down here. Let's have a look at this bit here. So as the ray comes up from water into air, you can see it's going from a more dense material to less dense. So it speeds up as it comes out and bends away from the normal as we'd expect. Now, if we can keep increasing the angle of incidence, remember that's θ1 or I, if we keep increasing that, we start getting to situation 2. And at a specific angle, which we call the critical angle, and we use C in your exam board to represent that, so just C, when it reaches that angle, what happens is it actually comes out, or it refracts at 90 degrees and goes along the surface. So we call that the critical angle. And this is the angle of incidence, so angle I, when R equals 90 degrees. That's the definition. Angle I when R equals 90 degrees, as you can see there. Now, what happens at above that angle is really cool. So when the angle is bigger than C, so let's say from water to air it's 42 degrees. Remember, you just look up in a book on the internet, or you can calculate it. I'll show you how in a minute. So when the angle is bigger than that, say this was the critical angle here, you can see that this angle is bigger than it. So when the angle of incidence is greater than the critical angle, that's condition 1, and 2, we've got to be going from more dense to less dense. So in this case, we're going from water to air, so we're going from more dense to less dense. If both of these are satisfied, we get total internal reflection. And this is what is happening in this image over here. The light's coming in, and instead of leaving the water, it's actually reflecting and following the laws of reflection. So this angle here, I, will be equal to R. It's following the law of reflection that I talked about in my first video, and it remains in the material. This is really useful because we can send pulses, as you can see in this image up here, we send pulses down through either glass or little fiber optic cables, and that's the basis of our internet. We send signals down these little thin cables that go under the ocean and under the earth, and they bounce off the interface, and that signal is the internet. It's also used in something called endoscopes. So we've got the communications, but we've also got endoscopes, which are medical devices that you can see inside the body without cutting open, and that's the basis of keyhole surgery. In one fiber optic cable, you can send light in so you can see. So it could be looking at knee, operating on the knee, you send the light in so you can see the knee, then reflects off the bit you're interested in inside the body, and that goes up back through another fiber optic cable for the doctor to see. And you need to know the basics of that for your exam. So total internal reflection is kind of well, it's not refracting anymore, it's reflecting and it's following the laws of reflection, and it's a special case when these two criteria, which you must learn, are satisfied. If you have to define what it is, well, it's where the light remains in the material, light remains in the denser material, so it does not escape, it reflects at the interface. Now there's one last thing we need to talk about, which is how do we work out C? Now you could do an experiment, often use a block like this, shine the light in, and you wait for total internal reflection to happen. So not there, maybe this one, oh yeah, there it is. And the moment when it starts doing that, that is the critical angle. But good news is, this is physics, so we have a really cool little equation. N equals 1 over sine C. That pen's cool, but you can't see it, so I'm going to write it out again. Remember, N is refractive index, we talked about earlier. C, in this case, is the critical angle measured in degrees. Don't get confused with this equation, where the C is the speed of light. So don't get confused with that. Goodbye. In this case, it's the critical angle. So if you know the refractive index, N, which you can often just look up, you can find out the critical angle, so you can find out when, apologies, just got cut off there, you find out when total internal reflection is going to happen. So that's how you can use that equation. And it is one of the ones you need to know. Units for critical angle are degrees, and remember, refractive index has no units. So let's go back up to our syllabus statements. Oh, we've done a lot there. Fraction is quite a tricky one, so do watch back any parts that you don't understand, and go on the internet yourself and try and find other videos or parts from the book to help you. So you can see now we've covered all these points. We know the meaning of critical angle. We know what internal reflection is. Just to mention about partial reflection. Now remember, when a ray comes out and refracts, you sometimes also get partial reflection. That's not total reflection. That's only when the conditions below are satisfied. We talked about the fiber optic cables, and we've talked about these two equations. Thank you for watching. We'll move on to other topics in future videos.